Hello and welcome to this lesson on exponential function. I'm Mohamed Kadem Kare. The PDF of the lesson may be downloaded from the website I indicate here. The outline of the lesson will be firstly to define the exponential function, then to state its basic properties. After that, I will show you the limits of the exponential function. And finally, we will show the relation of the exponential to the logarithm function. So let's begin by defining the exponential function. Here is the definition. There is a unique function f such that f is differentiable, f of 0 equals 1, and the derivative of f is itself. This function is called exponential, and we denote it either by exp of x or e to the power x. Here is the curve of the exponential function. So observe that exponential of 0 equals 1. Moreover, when x goes to infinity, here the function f, or the function exponential, goes to infinity. Plus infinity here, plus infinity here. And when x goes to minus infinity, the exponential goes to 0. I will go back later to these limits, but I wanted to show them on the figure from now. We now state the basic properties of the exponential function. These two properties are from the definition: exponential of 0 equals 1 and exponential of x prime equals itself. Moreover, we know that the exponential is always strictly positive. The third property says that the exponential transforms an addition here to a product. So the exponential of x plus y equals the exponential of x multiplied by exponential of y. Similarly, the exponential of a difference equals the ratio between the exponentials. In particular, exponential minus y equals 1 over exponential y. The last property here is very useful also. Exponential x to the power n equals exponential n multiplied by x. So try to keep in mind all these properties that are very useful in exercises. We shall now justify the notation of the exponential as a power. Remind that for integers, we have that n power p plus q equals n power p multiplied by n power q. And the property 1 of the exponential function shown in the previous slide shows that the exponential of the sum equals the product of exponentials. So you see the analogy between these two formulae, and in fact this analogy justifies the notation of the exponential as a power. And indeed, the exponential is really a power where the number e is a real number 2.718, etc. So this is a real number with some numerical value, and the first digits are shown here. Now we will solve equations and inequalities with exponential. The first property says that exponential of x equals exponential of y if and only if x equals y. Moreover, exponential of x is larger than exponential of y if and only if x is larger than y. These inequalities may also be large. And these properties are due to the fact that the exponential function is strictly increasing. We give now a formula on the composition of the exponential function with some function u, and we aim to calculate the derivative of such composition. Okay, remind that we have a general formula saying that if I compose a function v with a function u and I try to calculate the derivative, it will be u prime. So we firstly differentiate the interior function here, then we multiply by the derivative of the exterior function v and apply it to u. So as an application of this formula, the derivative of exponential of u will be firstly the derivative of u here, and perhaps erase this box. Okay, so I firstly differentiate the interior function u, which gives u prime, and then I differentiate the exponential, which gives the exponential itself applied to u. In particular, the derivative of exponential ax plus b will be a, which is the derivative of ax plus b, multiplied by the exponential of ax plus b. Let's now consider the limits of the exponential function. So remind that the curve of the exponential function is as follows, where here is 0, the value here is 1. So when x goes to infinity, the function f goes also to infinity. And this is this first limit here. Moreover, when x goes to minus infinity, the exponential function goes to 0, and this is the second result here. Now, if we try to calculate the limit of the ratio of the exponential function with x power p, where p is a strictly positive real number, then we have an indeterminate form. Since the numerator goes to plus infinity, the denominator also. So we have infinity over infinity, which is an indeterminate form. But we know in this case that the exponential prevails over any power of x. So in this ratio, it is as if there was only the exponential, so the limit is plus infinity. Similarly, if we try to calculate the limit of the power of x multiplied by the exponential when x goes to minus infinity, here this term will go to infinity and this term will go to 0. So it is also an indeterminate form, but again by the same argument, the exponential prevails over any power of x. This product here is as if there was only exponential, so the result will be 0, which is the limit of the exponential function. Here is an application of these properties. Assume that we have to calculate the limit of the ratio here of these two functions. So the idea, since there is obviously there is an indeterminate form, since each term here, this term goes to plus infinity, this term here goes to infinity minus infinity, so it is always an indeterminate form. So the idea is to factorize by the strongest term. The strongest term here is the exponential. Also here, the strongest term is exponential. So we factorize by this term, and we see that the exponential simplifies. And for the remaining terms here, we know since exponential prevails over any power of x, this term here will go to 0. Also, this term here will go to 0. So at the end, we get that the limit will be 1 over minus 1, which gives minus 1. Here is another limit which we may calculate with the help of the properties of the exponential function. Assume that we have to calculate the limit here when x goes to 0 of exponential of x minus 1 divided by x. So let's see together. This term here goes to 1 minus 1, which is 0. The denominator also goes to 0, so it is an indeterminate form, 0 divided by 0. Let's introduce the function f, exponential of x, whose derivative is itself. So the ratio here we have, for which we have to calculate the limit, is the rate of change of f between 0 and x. So by definition of the derivative, the limit of this rate of change as x goes to 0 equals f prime of 0, which is exponential 0, which equals 1. So the limit we are trying to calculate equals 1 by the properties of the derivative, the definition of the derivative, and the fact that the derivative of the exponential is itself. In the last section of this lesson, we will show the relation of exponential function with the logarithm. So here are the basic properties on this relation. The first property says that the exponential of the logarithm of x equals x. The second property says also that the logarithm of exponential of x equals x. In this case, we say that the exponential and the logarithm are inverse or converse one of each other. We say, for example, that the logarithm is the inverse function of the exponential, or the exponential function is the inverse of the logarithm. And indeed, if we try to solve exponential x equals y, it is equivalent to say that x equals logarithm of y. Here's an example of application of these properties. Assume that we have to solve this equation here with exponential. So we start from this equation. We apply the logarithm in both sides. So for the first term here, the logarithm of the exponential of x minus 2 equals x minus 2 by this property here. And on the right side, we have a logarithm of 3. So we get the value of x equal to 2 plus logarithm of 3. So the set of solutions is the singleton 2 plus logarithm of 3. And this ends this lesson about exponential function. I hope it was clear and useful for you. Good luck for your work on this material, and see you later. Goodbye.